Here in section 8.2, we're going to be looking at the basics of hypothesis testing. Now, this is going to be a foundational section for the rest of the semester. So looking ahead past exam 3, we're going to be working with t-tests, and then we're going to be doing correlations and chi-squares. All of these include doing statistical analysis within the framework of hypothesis testing. So it is absolutely essential for the rest of the semester, and indeed for using this material outside this course in your later classes, that you fully grasp the processes of hypothesis testing. So let's take ourselves through this one step at a time. Make sure that as you're going through, you're building a personal set of notes to help you solve these types of problems, adding in any additional information that you need to along the way. So let's get started. All right, a hypothesis is a claim or a statement about a particular property of a population. And then a hypothesis testing is basically the procedure that we use to test that claim and find out whether or not we have evidence to believe it's accurate. So keep in mind, when we're looking at these, the properties that we're discussing is most often going to be the value of a population parameter. So let's take a look at these real quickly and see if you can answer these questions. If I'm asking about a mu, that mu symbol, what does that go with? What population parameter is that asking about? Similarly, what happens for the lowercase p? What is it asking for? And what does my sigma ask for? Well, your mu should be solving for a mean. Your p is going to be a proportion or a percentage. Remember, they're the same thing. And then sigma is asking about my variation or my standard deviation. So we're going to focus here first on getting our hypotheses, interpreting them, and pulling them out from a particular problem. And we're going to use this example here on the left. So the first step that we're going to see is we need to identify the specific claim or hypothesis to be tested, and we need to put that in symbolic form. Now these are going to be the steps that are outlined in your book on figures 8.1 and 8.2. However, I am adding in some additional steps to help break these down. I suggest you include my additional steps in your notes as well. So when we're looking at this, we need to ask ourselves a couple of questions to solve this first part. First of all, what is the population parameter they are asking about here? So looking at this problem, what are they asking for? Notice they're asking about an increase in chance. So if they're asking about chance, which parameter are they asking about? Are they asking about my mean, my proportion, or my variation? They're asking about proportion, and that's going to be represented by the symbol p. So our problems here for both of our hypotheses are going to be centered on the symbol p. You would never have a situation where one of your hypotheses, your null, is regarding proportion and your alternative is regarding mean. So the property parameter, the population parameter for both your null and your alternative hypothesis is always going to be the same. Okay, so the next thing we need to do is what is the expected value if the intervention does not work? So if nothing happens, if this XOR method does not work here, what is going to be the expected value? With no intervention, the chance of having a girl is 50% or 0.5. So there's the answer for that particular question. Now, the part is we need to put these together in symbolic form. And this is simply going to look like this. So we're going to put p is equal to 0.50. So that's the claim that we're making. So when we're going through and we're looking at this, that's our first step. P equals 0.50. That is the claim or hypothesis that we're going to be testing. Now keep in mind what's important here, and we'll come back to this again at the end of this particular section lecture, is that we test the null hypothesis. So keep in mind we need to pay paying attention to language in terms of what we're testing. So the next thing we need to do is we need to give the symbolic form that must be true when the original claim is false. So if p is not equal to 0.50, then what is going to be the claim that we're going to make? I suggest you use this layout here to help you in making this formula. So you're going to have your property of interest, which in this case is p. You're going to have your direction of change. And if we look at this problem, what is the direction of change they are anticipating? Well, here we can see that they're anticipating an increase. So our direction of change is going to be greater than. So we have p is greater than, and then we have our amount, 0.50. So P is greater than 0.50. So that's our second step. And now we're on to our third step where we need to write these out in terms of the hypothesis formula. So here's where we are writing the hypotheses and we're putting them in statistical language. So you need to apply this rule of thumb. The null hypothesis represented by HO represents if no change, effect, or difference has occurred. Whereas H1, the alternative hypothesis, is if there is a change, effect, or difference. So which hypothesis fits with each specific symbolic claim? Well, as we can see, our null is going to be P is equal to 0.50, since that's what it would be without any intervention. And then our alternative is going to be P is greater than 0.50, since that is the alternative that they are proposing. So when we put this in hypothesis form, we get our null hypothesis is P equal to 0.50, and our alternative is P is greater than 0.50. So we've taken that original question they've been posing, does the XOR method increase the likelihood of giving birth to girls? And we've translated that general question into specific hypotheses of a null and an alternative in statistical language that we can now test. So notice here your alternative hypothesis is going to have the option carrying the non-equality symbols of greater than, less than, or not equal to. So pay attention there as well when you're setting up your null and your alternative. If you have your equal to sign in your alternative hypothesis, then something has gone wrong. Now let's take a moment and look at why we're bothering with our statistical analyses here. So we could say, looking at the observation of just the data alone, we could say, well, there's 58 is more girls than just 50, so does that show that it works? However, what we can't determine from this raw data alone is if this difference is outside the normal range of chance, right? So there's always a certain amount of variation around any particular value. So is 58 far enough away from 50 to say that that is exceptional and not likely due to be just chance alone with just the normal variation in the population? To be able to do that, we have to do our statistical analysis problem as we have laid out here. And kind of working ahead on this one for you a little bit, I went through and did the calculations, and our probability of having 58 or more girls in 100 births is 0.0548. Okay, now we're going to use this by applying our rare event rule, and if you remember, our rare event rule is looking for a value less than 0.05. So if we look at this here, our value of 0.0548 is in fact greater than 0.05. So 58 is not outside the range of chance. And when we collect our rare event rule back with the language, so notice we've been focusing kind of on the number 0.05, but now we need to make sure in hypothesis testing we connect that back with the language of the two given assumptions. So we have two assumptions in our hypotheses. We have the null hypothesis assumption that P is going to be equal to 0.50, and we have alternative hypothesis assumption that P is going to be greater than 0.50. So, as we see here, if under a given assumption the probability of a particular observed event is exceptionally small, we conclude that the assumption is probably not correct. Applying that to our hypotheses here, noticing that we test the null, so we're always testing the null hypothesis, so we're testing P equals 0.50. So notice that is, going back to the beginning, the claim that we're actually testing in order to infer support for our alternative claim. So if we look, we can see that connecting all of these pieces together, we would say if under the given assumption that P equals 0.50, since that's the given assumption we're measuring, the probability of the observed event from our data is exceptionally small, being less than or equal to 0.05, then we would conclude that the assumption is probably not correct and we would reject it. All right, so here we can see that 0.05 is in fact 0.0548 does not meet the criteria for being exceptionally small, therefore we do not reject the null hypothesis. So I hope that kind of helps you understand connecting the numbers from the rare event rule and that we're solving for in our statistical analyses. So we have our actual value that we've solved for, our p-value here, 0.0548, and we're comparing it to our particular goal of 0.05. Right, and assessing that. But keep in mind, it's also very important to be able to connect that clearly back with the language of the rare event rule, not just the pure number of 0.05, and make sure you're connecting the results with the given assumptions that we're testing in the particular study. Now, a moment here also to talk about when we're looking at being able to figure out what is the null and alternative hypothesis. And in fact, we're going to have the very next videos have a couple of practice exercises. So I'm going to touch on that a little bit more there because this has been a pretty dense lecture already. Again, make sure you've got this information from this particular slide embedded in your notes so that as you go along, you'll be able to do correct interpretations at the end.